Yeah, so my name is Shantanu Tuli. I'm going to talk about what I think is the next big challenge now that the lakehouse is maturing, which is optimization and management of a shared lakehouse across many different tools. So a little bit more about me. I've been working with data for, I don't know, something like 12, 13 years, starting with massive particle collision data sets, doing some NLP, as a machine learning engineer, and then just general data science and analytics and product strategy at data tooling companies. That's my dog, Ridge. She's contemplating the quark gluon plasma on my boat. Okay, so for today's talk, we're going to talk about the lakehouse vision and sort of how we got to the current state of the infrastructure. Then we'll talk about vertically integrated solutions that we've been using. And we'll discuss some of the challenges you face when there are multiple different tools interacting with a lakehouse. And finally, I'll propose a interoperable lakehouse design. So the shared storage vision is certainly not new. We've been wanting to have a unified storage layer for all of our different teams and applications, BI, ML, integrating some of our data back into the product. Making sure our data stores are auditable and all of that. And through our iterations, we've gone through warehouses, lakes, and now we're at the lakehouse. It's not the only motivation. Shared storage is certainly not the only motivation. We are also seeking better performance and more cost effectiveness. But it is certainly one of the things that we've sort of been pursuing on this journey to the lakehouse. And the lakehouse is getting us there. So I'm sure all of you are familiar with the architecture of Iceberg. We've got this data layer, data manifests. We've got metadata and snapshots, and then the catalog and pointers to the various different tables. And with this tree-based architecture, we are able to query from our different business functions into the same data lake sort of independently, sometimes even querying the same tables when we need to collaborate. And when I say query, I mean interacting with the lakehouse, not just retrieving data back, but also manipulating and such. So this works, is good, it's getting us there. But because of sort of how we got here, there are some expectations that we have from the lakehouse, justifiably, that we need to sort of reconcile with how we're doing things today. So in the warehouse, we've been used to reading and writing data from multiple different clients at the same time, and the warehouse sort of manages everything that happens in the background. It's doing its own thing. We're not really exposed to it, but certainly no one bats an eye if I and 5 other data engineers are querying the same data table or view at the same time. Now, now the difference is instead of multiple clients, we're trying to use multiple different tools that are sort of independent of each other. And at the same time, we expect our database-like qualities. As I said, we want to query, but beyond querying, we want to be able to create, drop, alter tables. We want to insert rows, update rows, manipulate rows. We want to do permissions provisioning, right? Granting access, et cetera. And we're expecting atomicity of an individual transaction in the lakehouse, including the ability to actually roll back to a previous state. It's a lot to ask of a data infrastructure. It's delivering, but it is a lot. So we have been building these vertically integrated tools that are different teams based on mostly personal preference are leveraging to interact with the lakehouse. So let's say these are 4 different, sometimes called query engines or processing engines more broadly, that are interacting with my lakehouse. And each of these query engines is going to have a connector to the lakehouse and have its own, have a model of the source data from the lakehouse, which it's going to use to plan and optimize its queries and then coordinate the workers to actually do the work. And this is sort of happening separately. So even when they're sort of touching the same tables, a lot is being decided and done by the processing engine. So in practice, what that looks like is when I I try to execute a statement or many of these different business functions through my processing engine. It's figuring out the how, and then it's going and doing the execution, and that execution can touch all the different layers of my lakehouse. So it's not just interacting with the catalog and returning something. It actually has the ability to change the metadata and the snapshots and the manifests and data files. So the challenge arises when we have this multiple users, therefore multiple engines, interacting with multiple tables in a very collaborative and sort of spread out manner. So for example, when multiple engines are working on the same table, we have concurrent reads and writes, something that we have to deal with. And data consistency across all of these different engines is extremely important, of course, non-negotiable, but it is difficult and it can be inefficient when a single engine can't stand out as the leader, as the voice of authority, like the warehouse did in its era, where what the warehouse says goes as far as how things are going to be executed. Now you've got different processing engines that are they can each do all the different things that you need to do throughout the data lifecycle, but no one's, they're competing against each other in some sense. Now, we do have to be able to support asset transactions and using through multiple tables when we have such a vision of a shared lakehouse that's like representing the entirety of my business for all my business functional units. An example of a single transaction that touches multiple different tables would be CDC, where I'm replicating a whole database that has maybe hundreds of tables underneath it, and it's committing all of that data every so often into my lakehouse. So it's certainly not it's a very common use case where multiple tables are being updated by the same time, and you have other engines that are trying to access that data or even update that data at once. So Iceberg, of course, has a way to deal with it, right? It distributes this sort of responsibility of ownership and maintenance across the different engines as much as possible, and the way it does that is through optimistic concurrency, which is achieved through snapshot isolation. And this is the idea where each writer and reader assumes that it's working in isolation, and in the reader's case, that's just saying that the reader will see a consistent snapshot while it's doing its work. And in the writer's case, it's going to take the latest snapshot. It's going to try to make all the changes, write out a new snapshot, and then try to commit that. And if it finds itself unable to do that commit because something else has come in and changed the snapshot, then it'll fail. That commit will fail. Then it'll go and grab the latest snapshot from whatever other engine has made the change, and then try the process again. And if that fails, try it again. This can get slow when we have high concurrency of events, which, for example, in a streaming data source where there are frequent updates due to the retrying of commits. So it's always a trade-off between performance and like how serializable you want your architecture to be, commits to be. And occasionally it can lead to deadlocks where maybe two engines are trying to do trying to update the same table, and every time one tries, it's stalled by the other, and so on and so forth. It's very rare, but that's the sort of situation you can run into when you don't have a voice of authority and rather multiple things are happening at once. So getting it right is tricky. Configuring the right concurrency control usually requires some domain expertise and should be done at the table level. So if I am let's say I'm in the analytics or BI team, I'm going to have some knowledge about which engine should be, or maybe let's not even think about the engine, like should have some context around what the table properties need to be, what is its retention time frame. How should concurrent writes be handled and stuff. So it really should be at the table level and not the engine level, which we have sort of become accustomed to. I want to mention that catalogs do play a key role in managing snapshot isolation. So this is not like an unsolved problem, but there are different catalog options, and not all catalogs implement the same procedures or in the same ways. So again, Iceberg provides a lot of functionality for optimization and data lifecycle management. So this includes the compaction, like the ability to compact small files within Iceberg, deleting old snapshots, cleaning up garbage, pruning manifest files, and it's got really good way to sort of use data filters on partitions so that you're not like necessarily scanning all the data, even when like you know ahead of the data file scan, you know, which might be relevant and which might not. So all of these things are really fantastic, but being that Iceberg is a table format specification and not as an engine, it is rightfully not authoritative about which procedure you should follow or which function you should use. It's not enforcing anything for you. It's sort of telling you these are the protocols that I support, these are the defaults, these are some other options as well, and you can sort of pick and choose. And so what happens is these engines go and pick and choose. That's how we configure the different options. So let's say, again, my BI team representative goes and configures their query engine, processing engine against Iceberg Lakehouse with certain properties. And then my ML team goes and does the same thing for their processing engine. Again, it's at the engine level, not the table level. So in a shared lakehouse, how do we deal with this issue of data lifecycle management at the table level? This is how we don't want to do it. So we don't want to do it at this sort of team level in an ad hoc manner where, you know, I run a query against a table, it's taking too long, and I'm like, oh, that's running too slow. Maybe I should go and compact this table now. Or I don't want to be like, oh, I don't need these snapshots anymore. I'm good from here forward, so I'll just delete the old snapshots. You shouldn't unilaterally make those decisions ad hoc because your decisions impact the other teams that are sharing this infrastructure, this lakehouse. These sorts of tasks should be scheduled and executed at the optimal cadence for specific tables, for each tables, which are going to be unique. The requirements are going to be unique. For example, if a table is being updated every 5 hours or something, you don't want to be compacting it every 5 minutes. But there are certainly tables that you would want to be compacting small files for every 5 minutes if you have a streaming source, for example. Even like concurrent write-retry interval, like how long should you wait if your write has failed because there was a competing one to try it again. These things are going to vary wildly by the table. The retention period, how long to keep data in a given table, is going to vary based on the kind of data. So even if you can agree on sort of general best practices for your lakehouse across all of these teams, which is, I mean, a near impossibility as soon as you go to enterprise grade and you have lots of teams, actually maintaining and implementing those policies, if you have all these different engines, at scale, gets difficult. So what's the solution? Here's what I think. I think we need to make the lakehouse interoperable, more interoperable across different engines. And the way to do that is by wrapping up my layers within a maintenance and optimization layer, for lack of a better word. So this system or engine, whatever it is, would be in charge of maintaining the data, manifest metadata files, and updating the snapshots. I'll go into more detail in the next slide on what sort of functions I'm looking for. But this is sort of the idea where you have a maintenance and optimization engine that's separate from other processing engines that are being used to access the data by different teams. So what do I mean by maintenance and optimization? One of those things is small file compaction. It shouldn't happen at the individual engine level. I should have a lakehouse policy per table around how often to compact small files. Dynamic clustering or repartitioning of data. So again, like it's really, the Iceberg offers a lot of hidden partitioning options. So it's it makes data access very efficient if you know how to do it right. And you shouldn't have to do it as a user, as an individual, as a data engineer. It should be, you know, a system that sort of is able to intelligently, dynamically repartition your data according to the best representation. based on the table's usage. Update delete consolidation. So this is an important one for streaming data sources, and I think about streaming data sources a lot, where when you have frequent updates, what happens is in a short amount of time, you might get a bunch of updates. And if you wanted to apply one at a time in a full transaction, that creates a lot of wastage. Like you create a manifest file for each update, and it's unnecessarily complex. Instead, what we can do is we can consolidate a bunch of updates in a certain window of time into one update file, and then apply that to the data. Data sorting is a fairly basic one, but also should not happen differently dictated by different engines, but rather as a set policy around how you want to sort your data for different kinds of data in your lakehouse. Table retention is another one. What is my table retention policy? I should be able to make that decision in a sort of collaborative manner and then implement that through this maintenance layer. And finally, file and metadata cleanup. Again, great ways to identify which files need to be cleaned up, but the actual execution of that, doing it, should be handled by this sort of maintenance layer. So with that, with this horizontally integrated engine, what we'd have is when I run a statement from any of my engines, it gets passed through that engine, but then the maintenance and optimization layer is what determines the how. So it's really doing all the scan planning, et cetera, and then passes that back into the processing engines, which then can do their execution through and through, no problems. That's it. I ran through that a little bit quicker than I intended to, but that just means more time for discussion. Yeah, that's the proposal for an interoperable lakehouse.